Hello everyone, and welcome to this 18th webinar, if I'm not wrong, of the Young Ceramics Network. And today it's the first one we co-host with the Bioceramics Network from ESERS. So first, I will briefly introduce and advertise the Young Ceramics Network. Then Maria Cannillo will also present the Bioceramics Network. And after, we'll have the two speakers. And finally, we will finish the session with questions. You can write all your questions in the chat, and we will ask them to the speakers. So first of all, the Young Ceramics Network. If I can share. Okay, so the Young Ceramics Network is an initiative of the European Ceramic Society and is sponsored by its journal, the JECS. And with the JEC Trust, the fund, we can receive a lot of money funding to bring together young students and professionals doing research on ceramics. So the YCN is really a non-profit association who wants to provide a platform for young researchers in order to build their own professional network and help them in their career. So to do that, we have a executive committee to keep the network alive and active. And for example, today organize webinars for you. So we are supervised by Erika Fernberg from Finland, who is the head of Young Ceramist and Training at ESERS. We are also helped a lot by Veronique and Donatella, ESERS administrative officers. And right now we have 5 young researchers in the committee, myself, Fawais, Alejandro, Sonia, and just recently Danica from Serbia. So this is a first map that we did some years ago about the Young Ceramics Network all over the world, but we are developing a new map that will be released very soon with a lot of new places where ceramics is going on. So the advantages of joining the YCN, of course, is to get help to attend professional events, make contacts, form links between the young researchers, but also with the industry. You can benefit from all this exchange to share ideas, experiences, and to get information about funding and job opportunities. That is very important for the career of young researchers. And all is the objective is always to promote research and innovation in the field of ceramics. So we have different platforms: Facebook, LinkedIn, Twitter, Instagram, and also very recent Discord. So you can just for free join all these platforms, and you are part of the YCN. You can also subscribe to our newsletter by email, and you receive every 2-3 months, more 3 months, a newsletter from the YCN where we share a lot of information. So as you can see on Facebook, we are now more than 1,200 members. So it's a very big community to share information, job offers, or get help for anything related to ceramics. It's the same in LinkedIn, but now we are a lot of members on LinkedIn with more than 1,600 members. So again, a very big community to share information. The more recent social networks are also a lot of members, and it's mostly used by the new members, the young ones. But we are also active on these platforms as Twitter and Instagram. So we are doing also different activities. So as I said before, the newsletter, the webinars like today. And we have also developed new things like the YCN representatives. Actually, we have now representatives of the YCN in a lot of countries when they can share the information, the activities locally in sometimes the language of the country. So we thought it was easier to connect the younger researchers. But we are also doing some student evenings. There's example in these pictures with during the last ESERS conference in Lyon, when we organized a student evening with, I think, more than 200 young researchers who join to share about their career, to have food, to have drinks, and to network together. We also organized a career fair in Lyon. It was very intense and very interesting to share with the industry. And in our newsletter, we also share research in spot to bring the research into focus and make it shine to the community and advertise the research of younger researchers. So here's a list of most of the webinars we organize in the past. So a lot of different topics, scientific topics, but also like soft skills or get funding for grants. So it's very broad topics. Here's a map of the YCN representative we have right now. So the selection of the new representative for 2 years is in progress. So we're still missing some representative for different countries. So if you're interested, you can still send your application to the YCN. Don't hesitate to connect with us. And if you're interested to join the network and be active, more active locally in your country. Yep. So we are looking to see you in real, let's say in 2 years in Germany for the next YCN Students Evening in Dresden. Very soon there will be information for the next YCN workshop. So this is a picture of the last workshop in Aveiro, Portugal last year. And for more e-source event, we have, for example, the Biocam next week in Belgium. You can still register, I think, until Friday. We have also electroceramics coming this summer, so you can still register, and also Shaping 9 in September in Poland. So yeah, as I said, the ESOS conference in Dresden also is in summer 2025. So stay tuned for more information. And last but not least, for the young researcher doing research on additive manufacturing, there will be the YCAM in May, next May in Tampere, Finland. So you can still register and submit your abstract. So this is a very nice conference, small format, but very interesting. So if you are doing research on additive manufacturing of ceramics, this is the place to go. So thank you so much, and I hope you will enjoy this great webinar on bioglasses. So now I will let the stage to Valeria Cannillo to present the Bioceramic Network.
Thank you, Nicholas.
I think you can now.
Okay. Thanks, Nicholas, for the introduction. And also the first thing I would like to thanks to the YCN to invite us for the organizing of this webinar, and also to take the chance to announce the activities that we are doing inside of this bioceramic network. First thing, I would like to no. You can see the screen, right?
Yes.
Okay, no.
Yeah, it's good.
In fact, the first action we launched was a logo design contest, and you can see the winner. We have a good number of participants in this contest, and the person awarded was announced in a conference devoted for young researchers working in bioceramics and bioglasses that take place in Madrid in May 2022. The second action we launched was a special issue in open ceramics. The name is Next Frontiers in Bioceramics, Improvements from Collaborative and Multidisciplinary Approach. The special issue was closed in September 2023, but I would like to invite you to visit this collection, because up to now we have published 15 papers focused in the last advances in bioglasses and bioceramics. Also, I would like to make a break. I don't know what problem is in class. Okay, perfect. Make a break about motivate you to publish your papers in Open Ceramics and the Journal of the European Ceramic Society, because apart to make diffusion about your research, you are contributing with JECTRAS. YCN is an agreement between both a journal and Elsevier, in which Elsevier return us part of the benefits, and we invest these benefits especially in young people. One important thing are the travel grants. You can see that tomorrow is the next deadline, but if you didn't have time to apply, don't worry, because there are 4 calls per year, and you can see here the different deadlines. The third action was to design of our website. I would like to highlight the definition that we give to our network. Our network aims to bring together scientists from academic, industry, and clinic working in the field of bioceramic and bioglasses. Why? Because we are trying to address the challenge to create a network multidisciplinary, with the aim to provide you a network for apply for European projects successfully, of course, and the research of this project get a real impact in the health of our society. About our network, you can see here the board. We have a good number of well-known researchers working around Europe. Between all of them, Paula Palmero is the leader of this network, and I have to say that I feel very honored to be working with all of them. You can see here some pictures about our first face-to-face meeting during the European conference celebrated in Lyon, and also about the Bioceramics 33 organized by Professor Mark Bonner, that is one of the members of our board. In the website, you can find also information about different international, European, and even national societies dealing with bioceramics. If you have any other information about different societies, please provide us, and we will spread this information in our website. Other important information you can find in the website is an updated calendar about conference focused in the field of bioceramics and bioglasses. For example, some of our board members were co-organizing different symposia during the last ISERS conference in Lyon in bioceramics, bioglasses, but about also dental implants. And today, of course, we are co-organizing with the YCN this webinar. I would like to highlight this workshop that already was mentioned by Nicolas, the first international workshop dedicated to ceramic additive manufacturing biomedical application, that is organized by the Belgian Ceramic Research Center and the European Ceramic Society, with the support of Europe's Make Ceramics, a network from ISERS focused in additive manufacturing, the bioceramic networks, and also YCN. I would like to keep you, ask you to keep tuned to our social media that I will present later, because soon we're going to launch an online speech contest for young professionals. The info will be delivered on December 2023. It's planned to be celebrated in 2024, and we will give awards to provide financial support for participate in conference. Also, I would like to mention some activities about technologies and expertise projects or pick-up research that you can find in our website. You can see a subsection in technologies and expertise. Sorry. If you want to deliver information about that, you only have to participate in the call for website contribution. With this call, you can share information within our community about activities carried out in your laboratory or company, inspiring technology or expertise, exciting projects, or a nice picture from a recent paper. You only have to download You only have to download the template that is available in the website in the section news, call for contribution, and submit to info@iser.org. The good point is also we spread this information in our social media. You can see here a couple of examples already announced and posted in social media. And why to follow us in our social media? Because apart to keep updated about website contribution, you can find information about different conferences and events, professional opportunities, and news in the field of bioceramics and bioglasses. So please follow us in the different channels that we are announcing all our activities. Thank you so much.
So now we can welcome our first speaker. Valeria Cannillo is full professor of material science and technology at the Department of Engineering Enzo Ferrari, University of Modena and Reggio Emilia in Italy. She leads the biomaterial research group of her department, and her scientific activity is focused on computational methods and experimental investigation for the design and optimization of innovative materials, with a special focus of bioceramics, bioactive glasses, and their composites for bone and soft tissues regeneration. She has led several research projects, and she was listed in the world's top 2% scientists from Stanford University in the US. And currently, she's specialty chief editor of Frontiers in Materials, section Ceramics and Glass. Professor Cannillo, the stage is yours, and thank you again to give us the honor to do a presentation today. I think you are muted. Your mic is not on.
Sorry,
yeah. It's good. It's good.
Okay, so I was saying thank you very much for the nice introduction. It's my pleasure to be here today, so thank you for your invitation. Just let me put in full screen. Okay, in this talk today, I will illustrate the possibilities for bioactive glass to regenerate hard and soft tissues. Since their discovery at the end of the 60s, bioactive glasses have become widely studied materials because they open new scenarios in the field of bone tissue regeneration and repair. In fact, such materials have an important property which is not easy to find. Once implanted in the human body, bioactive glasses are not only well tolerated by bone tissue, but they are also able to form a strong chemical bonding with bone. 45S5 bioglass was the first bioactive glass produced by Professor Enge, and it is able to bond both hard and soft tissues. Moreover, 45S5 stimulates angiogenesis, vascularization, and it has an antibacterial activity. However, bioactive glasses have shown some drawbacks, in particular their tendency to crystallize during thermal treatments. But such thermal treatments are necessary in several processing routes, such as the production of sinter materials, coatings, and scaffolds for bone tissue engineering. Besides slowing down or inhibiting the sintering process, the partial crystallization of a glass may reduce the biological performance of a final product and lead to implant instability once placed in the body, because the residual glassy phase is degraded preferentially. Moreover, it should be stressed that the regenerative potential of bioactive glasses is strongly influenced by their ionic release, which may be too slow in partially crystallized samples. Unfortunately, the optimal sintering temperature for 45S5 is between 1000 and 1100 degrees to realize scaffolds. So the crystallization temperature is reached, and so there is a wide devitrification of the system. This is the reason why in our group we have designed and produced novel bioactive glasses. Such glasses are characterized at the same time by very high crystallization temperatures and improved biological performance. The high crystallization temperature is designed in order to avoid the formation of undesired crystalline phases during the thermal treatments. And at the same time, adding to the glass composition the so-called therapeutic ions, it is possible also to improve the biological performance with respect to the 45S5 original composition. Thanks to this combination of properties, such bioactive glasses are so suitable for the production of sintered products, such as scaffolds, composites, or bioactive coatings. So, the new composition are characterized by a lower content of alkali oxides with respect to 45S5, and this was done to increase the crystallization temperature. So, there is a high ratio of calcium oxide to sodium oxide. And then the biological performance, as I mentioned, is improved by adding therapeutic ions, in particular magnesium and strontium. Magnesium is essential to bone metabolism because it stimulates new bone formation, increases bone cell adhesion. And in addition to this, it is used to modify and improve the thermal, mechanical, and physical properties of silicate glasses. On the other hand, strontium is able to stimulate osteoblasts, and at the same time, it inhibits osteoclast. Here, the two main compositions are reported. We worked on several different systems, but today I'm showing you only the two best ones. So you see that you have magnesium oxide and strontium oxide. The bioactive glasses have been prepared in different forms. So first of all, in powder forms for the thermal characterization by means of differential thermal analysis, DTA, and heating microscopy. And then they have also produced in the form of discs by sintering to verify the sintering attitude and then verifying the bioactivity and cell behavior. And then they have produced also in granules in the range 250-500 microns for the complete biological characterization. And as I will illustrate in the following, also for in vivo implants. So here you have the characteristic temperatures of bioglass, and as you can see, you have an extraordinarily high crystallization peak, which is about 932 degrees, which is one of the highest ever reported in the literature. But what is more important to note is that for this glass, you have a very large sintering window or processing window, call it as you wish, which is the difference between the onset of crystallization and glass transition temperature. So in this glass, you can produce sinter sample with no crystallization, but I will verify it later, I will show you. Just for reference, the crystallization peak for 45S5 bioactive glass is between 650 and 690, but this bioactive glass can be sintered only at 1100 degrees. So you have an extensive devitrification. You have many crystalline phases. So to verify that it was possible to produce sinter products, glass powders were pressed in disc to form green bodies and then were heat treated at the sintering temperature determined by heating microscopy. And here you see the XRD analysis on sinter disc. As you can see, you have only the amorphous halo, so the product is completely amorphous with no crystalline peaks. On the right, you have also the SEM images on cross-section of a sintered glass, so you can see that the sample is fully sintered, apart some residual, very small residual porosity. And so this demonstrates that it's possible to sinter the first glass BGMS10 with no crystallization at all. Just for comparison, here you have a sinter 45S5. It was necessary to sinter it at 1050 degrees for 3 hours. And from the spectrum, you see that while the starting bioactive glass is completely amorphous, once you sinter it, there are many, many crystalline peaks. The first glass, the BGMS10, biological performance was evaluated by immersion in SPF, simulated body fluid, by cytotoxicity tests following the ISO norm 10993 and using a 3D innovative cellular model that mimics the potential clinical application of a biomaterial. So this model was applied for the first time to a bioactive glass and was reliable because it used human bone marrow mesenchymal stem cells. And the model was fully 3D. Usually cellular models are two-dimensional. This is 3D. But let's start with immersion in the Kokubo in SPF, in simulated body fluid, according to the Kokubo protocol. So in view of a biological characterization, the granules has tested in SPF. SPF is in a cellular solution with ion concentration analogous to that of human blood plasma, and such protocol has been reproposed recently also for granules and powders. And in the picture, you can see the BGMS-10 granules after immersion in SPF for increasing times. Just after 1 day, the surface is characterized by several cracks. And after 7 days, it is possible to observe the formation of white globular precipitate, which are typical for hydroxyapatite. The results of EDS analysis performed on the precipitate found a calcium to phosphorus ratio of about 1.67, so it is the stoichiometric value of hydroxyapatite, and thus confirming the bioactivity of the BGMS-10. So, coming to the biocompatibility, according to ISO norm, the biocompatibility was tested with the L929.
Valeria, I'm sorry, but we cannot hear you, or we cannot
It
hear
seems
you.
there is like a network issue.
Yeah, she's disconnected. Well, she's still connected, but
maybe we can wait to see connected again and say that stop the video. But
the
the
problem is maybe she does not see that she's disconnected. So I'm going to, yes, I stop the screen share. Ah, Valeria, are you back? Um, Sorry about this.
And maybe we can send an email or
Maybe in the chat, but
she's gone.
yeah, she's gone.
Yeah,
Hopefully she's come back. How do you say ce sont les joies du direct in English?
Choice of live stream, I guess.
Maybe it will be great for next webinar to have the telephone number of the speaker.
Yeah.
Write
Good
them
idea.
directly.
Maybe Nico, can you present orally, as you did not before, the way we're going to act with the questions?
Yes, so if you have any question, you can write in the chat. And after the two speakers, we will ask the questions to the speakers and then they will answer after the two speakers. Yes. We hope that Valeria will be back very soon.
If maybe we have to wait more than a couple of minutes, we could start with Marcela, and if Valeria joins later, we can continue after.
Sure, yeah.
I will send her an email to inform her.
I just sent her an email.
Okay, perfect. Okay, so Marcela, you can share your screen if you wish.
So is Marcela is ready? We can so we say welcome to her and thank you to accept to present your work in our webinar. So Marcela Arango Ospina is a PhD student at the Institute of Biomaterials at the University of Erlangen-Nuremberg in Germany. Her research activities are focused on the biological evaluations of silicate-based bioactive glasses and silicon oxycarbide materials incorporating metallic ions, interesting for both generation. She has also worked on the production of bioactive glass scaffolds using different manufacturing techniques and investigating additional functionalities by polymer coatings. So Marcela, thank you again, and the stage is yours. We hope we don't have any issues connection.
Yeah, let's hope that. Can you hear me and can you see my presentation in the right mode?
Yes, perfect. Everything is good.
Okay, perfect. So good afternoon, everyone. First, I would like to thank the organizers for the invitation to this webinar, which I must say I was always the person attending this kind of webinars, and now is yeah, quite an experience to be presenting.
Sorry. Okay, sorry, I'm back. I don't know what happened to me. I was kicked out of a meeting. I'm really sorry for this, but I don't know what happened.
No problem, Valeria. No
Shall
problem.
I just stop sharing and we continue with Valeria's presentation, or?
Oh, yes, we can continue with Valeria's presentation if you don't mind. And we go back to you after that.
I don't know what happened. I'm sorry. I was talking to myself at a certain point. I
Yes.
realized I was not connected.
You had trouble with the internet connection, and then
I don't know, because it worked. It seems it worked fine. I don't know. I really apologize. I don't know.
No problem.
Did you get until here? I guess.
Yes, I think that's the last slide we saw.
Okay.
Maybe for the rest of the presentation, you can turn off your camera like
Yeah,
this. You have better connection, and yeah, will be, I think, better.
Yes. Okay. Just let me turn off the camera.
Okay.
Okay.
Okay, great.
Okay. So I hope no more problems. I'm really sorry.
No problem.
Okay, so I was saying that we performed an osteogenic differentiation assay by adding a mix of growth factor to the expansion media, and then we used alizarin red staining to detect calcium deposit in the mineralized matrix. So the induced culture were completely positive to the staining. As you can see here from the round bright red structure, which are calcium deposits. But which is more interesting is that also culture maintained only with the expansion media resulted positive to the staining. So this underlines the ability of the material itself to induce cells toward an osteogenic differentiation, probably due to the modification and dissolution product of the materials. So the ions released during the culture stimulated the stem cells to differentiate, even in the absence of proper growth factors. So this underlines a very strong osteoinductivity and osteoconductivity of the material itself. So the same study was repeated also on the other glass with BioMS. So I will go quickly through these slides. So you see again the characteristic temperature, very high also in these cases. The samples are completely amorphous even after sintering. The SPF test is positive. The biocompatibility is fully guaranteed. And also the assay with the stem cells gave positive results. The cells were able to adhere and colonize the material. And also the osteogenic differentiation assay was very, very nice. And again, the cultures maintaining only with expansion media, so without the growth factors, resulted positive to the staining. So due to the very good combination of properties, this second bioactive glass, BioMS, was patented. But anyway, both BGMS10 and BioMS were used for hard and soft tissue applications. So in this talk, I will illustrate some research that our group has performed, both for hard tissue application like orthopedics and dentistry, and soft tissue application. As far as hard tissue application are concerned, I will show you in vivo implants of bioactive glass granules, then the production of scaffolds, of coatings, of composites, and the production of dense sample by spark plasma sintering. For soft tissue application, I will show you the production of wound healing systems containing bioactive glasses, and then of 3D printing of composites loaded with bioactive glasses. So before proceeding with in vivo implants, we performed a molecular dynamics study, which is very useful for glasses because it permits to analyze the behavior of the glasses based on the composition. And it was demonstrated that the higher thermal stability of these novel bioactive glasses could be ascribed to several different factors, such as the increased chemical disorder of a network, the introduction of magnesium in the network, in the silica matrix, and the reduced amount of sodium which is required to crystallize some crystalline phases. And the different reactivity of the glasses was interpreted by analyzing the glass surfaces in terms of concentration of atomic species, coordination number, and QN species. And we observed that with respect to the 45S5 glass, this new composition presented thinner surfaces with a reduced sodium concentration, which is beneficial for cellular uptake and differentiation. So here you see the implants of bioactive glass granules. Such granules, both of BGMS10 and BioMS, were implanted in rabbits. So in rabbits' femur up to 60 days. And 45S5 granules were implanted as well as a reference. Here you can see the SEM scanning electron microscopy images of 45S5, BGMS10 and BioMS after 30 days and 60 days, where you can see the bioactive glass granules, but also the bone trabeculae and the soft tissue. And here, for example, you have some zoom still evidencing after 30 and 60 days some residual bioactive glass granules. But we also had EDS maps for showing the distribution of silicon, which is representative of both glass and silica gel, and of calcium, which is representative of hydroxyapatite or bone tissue. And more interestingly, here you have histologies. So these are light microscopy images of a section of a bone of rabbits after 30 days, and you see new bone trabeculae. And here you have the same kind of analysis after 60 days. And it was interesting to observe that after 30 days, so after 1 month, All the bioactive glasses, including 45S5, displayed a similar behavior in terms of bone amount, bone thickness, thickness of new bone trabeculae, and affinity index. However, after 60 days, 45S5 granules were mainly surrounded by wide and scattered bone trabeculae, separated by large amount of soft tissue. On the other hand, in BGMS10 and BioMS, the trabeculae were thin and uniformly distributed around the granules, and this can be considered as more advantageous since the two novel glasses allowed for the neoformation of a uniformly distributed bony trabeculae, which are predictive of a more favorable mechanical behavior compared to the less uniform coarse trabeculae in 45S5, and this permits us to conclude that BGMS10 and BMS could be considered as suitable products for tissue regeneration in the orthopedic and dental fields. So, with these two novel glasses, we produce scaffolds. These are scaffolds produced by a very simple technique, the replica technique, and we produce it using 45S5, but also the two novel bioactive glass. We obtained so far good in vitro results. So for biological tests, I will not show you everything because otherwise it's too long, but trust me, the results were good. And currently such scaffolds are implanted in vivo in rabbits up to 60 days. And we are waiting for these results in the next few days. So I'm afraid I cannot present the in vivo results, but I will be able to do that soon. Then we also produce composite scaffolds, using also different polymers such as PHPV, PLA, PCL. And these scaffolds this time were produced by thermal induced phase separation method. And such scaffolds were reinforced with bioactive glass, but also with hydroxyapatite and calcium silicate for comparison. We obtained good in vitro results, and the better performance was obtained with the bioactive glass. So this is very good. And still for these glasses, so we have only in vitro results and still need to implant them in rabbits. We produce composite scaffold also using 3D printing, so a different technique. And here are the results also of the microstructure. Also in this case, the in vitro tests are very encouraging. For example, with tests such as Alamar Blue or LDH assay. And then we produced also coating using the first bioactive glass, first novel bioactive glass BGMS10. We produced coating using atmospheric plasma spraying. Atmospheric plasma spraying is a technique in which you have a torch. The powder are injected in the torch. The bioactive glass powder melts inside the torch because the temperature is very, very high, like 1000 of degrees Celsius. Then such molten particles are projected onto a substrate. During the flight, the particles cool down, and when they impact the substrate, they solidify, giving rise to lamella structures. So you can find the surface and cross-section of such coatings with different processing parameters. And so you can see varying some parameters of a torch, you can obtain different results. These coatings are particularly useful, for example, to coat a metallic prosthesis. And also in this case, we have results in vitro. So for example, in SPF and cellular results, which are encouraging, but we don't have yet in vivo results. Then we use also spark plasma sintering. Spark plasma sintering is a technique based on a pulsed electric current which flows across a conductive die. The die contains the powder which should be consolidated. So such powders are rapidly heated by Joule effect, and at the same time a compressive load is applied. And so due to the milder condition, several beneficial effects can be obtained, such as to avoid or limit decomposition and crystallization phenomena. And with this technique, you can obtain fully dense products. So you can see products obtained with BGMS10. And of course, depending on the processing parameters, some crystallization was obtained in some samples, while some other samples were completely amorphous. Also in this case, the in vitro results were very good. And we produced also composites with hydroxyapatite, and this was done to tailor the dissolution rate because, as you know, the dissolution rate of bioactive glasses is much more faster than the one of hydroxyapatite, so you can tune the dissolution rate building a composites. And also in this case, the tests in SPF were encouraging. Then coming to soft tissue application, first of all, we produce gauzes for wound healing. So we started with a commercial gauze, which was impregnated with chitosan and bioactive glass. We use different compositions, so as everywhere, 45S5 as a comparison, as a reference, and then BGMS10, and also BGMS10 modified with addition of zinc, which is a ion known for antibacterial effect, and antibacterial effect is devised for an application like skin regeneration or a gauze, or so to avoid infections. And in this case, the gauzes were tested in vitro using a very simple test, which is the scratch test, in which you produce a scratch and then you see when the scratch is closed. And in the graph, you can see the cell migration rate after 24 hours and 48 hours. And so as you can see, the gauzes produced with the novel bioactive glasses gave very promising results. Then we did something with to regenerate difficult wounds, such as of people with diabetes or something like that. And in this case, we produce skin patches using 3D printing. And we printed collagen plus bioactive glass, which was the BioMS or 45S5. And which is interesting, we used human skin. This human skin came from surgery, from abdominoplasty. So the surgeon gave us this human skin that we treated. First of all, we treated with SDS, sodium dodecyl sulfate. Sodium dodecyl sulfate, SDS, is a skin irritant. So the skin was artificially damaged in order to see if the patch containing the bioactive glass was able to heal the skin. And so you can see the histology from skin. In the upper left, you see an healthy skin, where you see in the bottom the dermis, and in the upper part the epidermis. On the right, you have the SDS treated skin, where you can see the damage. You can see the pycnotic nuclei of keratinocytes, so this means damage. And then we put the patch with scaffold with BioMS and the 45S5. In both cases, we saw skin healing, which was better for BioMS. So this is a preliminary results, but still very important because done with human skin. So it's not a real in vivo test, but is done with a human real skin. So concluding, these novel bioactive glasses were characterized by very high crystallization temperature and at the same time improved biological performance with respect to other bioactive glasses in the literature, also in vivo. And this was due to the addition of therapeutic ions such as strontium and magnesium and other ions. And thanks to the very high crystallization temperature, a large processing window was obtained with a very high crystallization peak temperature. So these bioactive glasses are ideal candidates for the treatment, for thermal treatment. So for the realization of products whose processing require thermal treatment, such as scaffolds or coatings or sinter products. Such glasses were tested with human bone marrow mesenchymal stem cells and also in vivo in rabbits. Then for hard tissue, we produce scaffold, coatings, composites, and spark plasma sinter samples. And for soft tissue, we produced also gauzes for wound healing and 3D printed skin patches. So future work will devise for sure the in vivo implants, all these products, because for the moment we have only implanted the granules and the first scaffolds I show you. So in animal, and then of course clinical studies. And also we need in vivo tests for soft tissue. Before concluding, please let me thank all the people who collaborated with me in this research, so some colleagues from my university, but also from other university, and thank you very much for your attention.
Thank you so much, Valeria.
Thank you. Sorry again for the problem with the connection. I hope that now works fine. I don't know what happened. It never happened to me, but of course, you know, when you have to deliver a talk, it happens that day. But
no worries at all. No worries. It happens.
Okay.
No worries. Thank you. So now we can welcome again Marcela for a talk about bioglasses. If Marcela is ready. Yeah. Sorry again, Marcela, for the previous.
Yeah. No problem.
Marcela.
Okay. Hello again, everyone. So today I will give you an overview of the enhancement of bioactive glasses with therapeutic ions and herbal medicine. So as Nicholas mentioned before, I am a PhD student at the University of Erlangen-Nuremberg under the supervision of Professor Aldo Boccaccini. So first of all, I would like to show you where the university is. So the FAU is located in Erlangen in the state of Bavaria in southern Germany. So as you can see in the map, Erlangen's location in Central Europe makes it well connected to various countries, which is an advantage also for the internationalization of the uni. And about the FAU, we can say that it's one of the largest universities in Germany, and it proudly holds the #1 place in ranking for innovation and also for citations. Numbers which I'm sure our materials department is helping a lot with. And as every city in Bavaria, we have here evidence of the beer festival. So you all are also welcome to visit Erlangen for this. So in this talk, I will start with an introduction to bioactive glasses, then go to some commercial products and applications, then move to the functionality by modifying with metallic ions and herbal medicine. And I will finish with a case combining bioactive glass scaffolds with Manuka honey. So we cannot start talking about bioactive glasses without mentioning Larry Hench, who was the inventor of the first bioactive glass composition, as Professor Valeria mentioned before. And as you could see, this is still one of the most used compositions, especially as reference material. So at that time, Hench was challenged by someone in the US Army to get a material which could prevent the loss of limbs, since usually the polymers and metals that were being used at that time were rejected by the body, so doctors usually needed to amputate. So then he got the funds and started the research, and after getting the first composition that the team thought might work, this was implanted in rats. And then when the surgeon tried to remove it, he couldn't. So that's why they realized that they just got a material which could bond very strongly to bone. So of course, this marked the beginning of a new area in which the constant research on new compositions is, it's happening. So in this slide, I just want to summarize again this effect of bioactivity, which usually this is the way we characterize this strong bond to heart tissue. And this is usually evaluated in simulated body fluid. So what happens is at the beginning, when it gets in contact with body fluids, a series of reactions start. So first, the breakage of the silica network, then the formation of the silanol on the surface, followed by the formation of the silica-rich layer. And then we had the migration of calcium and phosphorus from the solutions, which forms the precipitation of an apatite-like layer, which later on crystallizes to hydroxycarbonate apatite. So on the pictures on the right, you can nicely see these layers of the silica-rich layer and also the apatite layer on top. So as mentioned before, bioactive glasses bond to hard tissue. So in the clinic, these are usually applied as granules. And here there is an example of a commercial glass from Bonalife, which has a similar composition to 45S5. And this has shown to combat bone infections. So on the right, we can see an study case in which a defect caused by a very chronic bone infection was filled with bioactive glasses, and then after 2 years, we can see a successful recovery with almost no particles left. So as we could see in the previous talk, bioactive glasses are not only designed to regenerate hard tissue, but also soft tissues. So this is done mainly by the dissolution products of the glass, which stimulate biological processes in cells, so like accelerating the epithelial cell migration or proliferation, which is important for wound healing. So it has also been studied the production of glass fibers, which look like cotton-like structure. So as we can see in the video that is being played right now, so these fibers can be produced via the electrospinning technique, in which a solution is pumped from a needle and expelled towards a collector. So both needle and collector are under a high voltage, a very high voltage. And during this process, the solvent evaporates and the fibers form on the collector. So in here, we can see how the final fibers look like. So it's really like cotton. And yeah, this is usually the idea is to apply it as wound dressings, for example. Okay, here we can find some examples of commercial products with bioactive glasses. So we have granules which are usually mixed with binders, so to form kind of a paste. And then this is usually used for small defects. We also have toothpastes in the market which claim to protect enamel, and also to reduce the sensitivity in tooth. And in this case, Biomine is shown, but also Sensodyne has a line with bioactive glass particles. And lastly, this is a commercial product, including fibers. So the name is Miragen, and this is made out of borate bioactive glasses, and it's especially for wound healing, and it has been used in ulcers, for example, for diabetes. Okay, so we have seen that bioactive glasses are versatile materials, and this is due to the possibility to design their composition according to the functionality we want. So this is done by incorporating therapeutic ions such as strontium, copper, zinc, magnesium, boron, which will have an effect not only on the glass properties, but also will lead to different biological responses. So for example, if we want to have an antibacterial effect, then we could add zinc or copper. But if we are interested in stimulating the formation of new blood vessels, then we consider, for example, boron. But there are also elements which could have dual or multiple effects. So for example, zinc can stimulate bone formation, while can have also an antibacterial effect, for example. So with this approach, the functionality of bioactive glasses has been quite expanded. So, and one example, I show it in this slide. So a very important property of bioactive glasses is their potential angiogenic effect. So angiogenic is the process in which new blood vessels are formed from existing ones. And it's a key process in wound healing and tissue regeneration in general, because it has an important role in the transport of nutrients and waste. So our institute has explored this effect in cooperation with the medical school in Erlangen. So in this case, an arteriovenous or AV loop model was used, which is an in vivo tissue engineering approach for generating vascularized tissue. So in this AV loop is placed into an implantation chamber. So in this case, we can see that it's made out of Teflon. And then this chamber is filled with bioactive glass granules mixed with fibrin, for example. And then in this specific case, copper doped 45S5 was also used. So this was implanted for 3 weeks. And then, vascularized tissue is formed. And the parameters such as vessel density or vascularized area are measured. And here we can see that for the glass with copper, these values were higher compared to the reference composition. Also, recently we published a review article, which summarizes the use of what we called exotic or less common ions in bioactive classes. And in here, we included also rare earth elements, for example. So we consider different functionalities, for instance, bioactive behavior, antibacterial effect, cytotoxicity, mechanical strength, radiation shielding, photoluminescence, and we could identify the potential use of some elements that could not only provide a therapeutic effect in terms, for example, of photoluminescence, which is quite important, but also stimulate biological processes to regenerate tissue. So, of course, there is still the need of more studies, mainly involving in vivo or more biology, to really draw conclusions here, for example, at long time evaluations. Moreover, here I just want to show the other type of bioactive glasses apart from the melt-derived ones. So these are salt gel glasses, which are characterized by their high surface area and porosity, which you can also tune in terms of ordering, for example. And this provides glasses with the possibility to add biomolecules to act as drug carriers. So therefore, here we not only have the properties of the conventional bioactive glasses, but also we can have the release of therapeutic agents. So now I will move and introduce the topic of herbal medicine, which has its origin in Asian cultures, and it involves the medical use of plants to treat disease and enhance general health and well-being. So the science behind herbal medicine is rooted in the study of phytochemistry, pharmacology, and traditional knowledge. So in phytochemistry, we consider the active components like flavonoids, for example, and it is known that herbal medicine often contain a complex mixture of compounds, and usually the synergistic interactions between them can enhance therapeutic effects, but also minimize the potential side effects. So this is quite important for this kind of materials. In pharmacology, we should consider the bioavailability, which means to understand how the body absorbs, distributes, metabolizes, and also how it eliminates the herbal compound. So factors like preparation, dosage, and interactions with other substances are also considered here. And additionally, the identification of mechanisms of action is key. So this includes identifying molecules or targets, receptors, and signaling pathways that these active compounds can have. So moreover, traditional knowledge also plays a role since it became the basis for many treatments. So for example, in the traditional Chinese medicine, so also performing endobotanical studies allow us to understand the use of plants by indigenous cultures, for example, and then help us to elucidate their cultural significance. Then other aspects that we should consider here are safety, so which includes assessing the potential toxicity, interaction with other medications, and then establishing these the safe dosage levels. And of course, regulation should be considered to ensure quality, safety, and also efficacy. And finally, the scientific evaluation should be performed. So this includes clinical trials, laboratory studies, and also the establishment of standardized processes that we can ensure consistency, quality, and also in the dosage that we apply them. So in this context, the approach to combine bioactive glasses with phytotherapeutics is being considered. And the main reason is to use the potential synergies between them, and especially to extend the functionality of bioactive glasses. So the hypothesis is that herbal medicine may contribute additionally with benefits, therapeutic benefits, for example, anti-inflammatory or antimicrobial properties. And this could complement the regenerative effects of bioactive glasses. So potential applications have been reported in different scenarios like wound healing, tissue engineering, orthopedics, and but as mentioned before, there is still challenges like optimizing the formulations, ensuring this compatibility, and understanding the precise mechanism of interaction between both materials. So not only the mechanism of action of the herbal compound, but also the mechanism of action when both are combined. So when using bioactive glasses, different strategies are considered. So depending of the method that the glass was produced so for example, we can have melt-derived glasses or granules or scaffolds, and then the idea is to link these phytotherapeutics to the surface. And then what is expected is that during the dissolution process of the glass, the therapeutic ions are released from the glass structure, and then at the same time the active compounds of the phytotherapeutics are being released. So of course this process happens at the same time as the protein absorption on the material, and also the formation of the apatite layer that we saw before. So on the other hand, we can have the mesoporous glasses, which are produced via the sol-gel method, and these will be the carriers of the phytocompounds, and hopefully we expect to have a controlled release of the plant compound, but also on the ions. And of course, here is also the challenging part of this topic. So some examples of phytotherapeutic compounds in combination with bioactive glasses are shown on the right. So, for example, curcumin is known for its inflammatory and antioxidant properties. Then we have this Yunnan Bayao, which has shown the anti-inflammatory and hemostatic properties, and this has especially been used in ointments for diabetic ulcers in combination with bioactive glass particles. Then we have neem, which is antibacterial and anti-inflammatory, and also it has antiviral properties. And for this plant is quite special because every part of the plant has been used for different applications, so the flower or the bark or the leaf. But the extracts of the leaf have been the ones combined with bioactive glasses, especially for their antibacterial effect. And then we have also propolis, which its main active compound are polyphenols, and this has been widely studied, or more than others, and it has shown properties like antibacterial effect, antifungal, anti-inflammatory, and so on. So this has been quite reported in the literature, let's say. Then Icarin has been also studied, and in combination with bioactive glasses for the treatment of bone diseases. Also, it has shown some angiogenic effect. And then we have a gallic acid, which is antioxidant and anti-cancer. And then we have, polyphenols, which this is kind of one of the main active components of a lot of natural products. We have essential oils, which have been shown anti-inflammatory properties, antibacterial effects, and then we have manuka honey, which I will show later on. So in summary, the strategy of using these phytocompounds and bioactive glasses led to combined therapies to treat wound healing, to reduce inflammation at the application site, and also reduce infections during the healing process. So if you wish to have more information on this topic, you are welcome to check out these two publications from our group, which have a very comprehensive information about this topic. And now I would like to point out some studies, so just as examples, so that you can see different examples of when bioactive classes and herbal medicine have been combined. So in this case, this group combined Mesoporous bioactive class with propolis and cranberry. This paper focused mainly on how is the incorporation of these natural products in the mesoporous glass particles, and then they focus on analyzing if this was affecting the bioactive behavior of the particles, which was not the case. So they didn't observe any negative effect on the bioactive behavior. Then another group studied the incorporation of curcumin, also in mesoporous bioactive classes, and here they also produce glasses with different ions. So they also wanted to see the effect of adding curcumin in glasses with different ions, or at least to see if there was a difference or if they had the same effect. And indeed, they found out that, for example, when they added zinc in the composition of the glass, the loading efficiency was not as good anymore as with the other ions. And also they kind of work on the release of the curcumin from these particles. And they mentioned that they saw two kind of effects. So one was the physical absorption on the normal one that occurs usually, but then they also observe an interaction between the curcumin and the ions. So this effect they didn't see in the mesoporous glasses that were without the ions that they incorporated. And as many studies suggest, when you use mesoporous glasses, there are two stages for the release. So the first one is for the products that are on the surface of the particles. So this is kind of the first release that occurs. And then there is a second one which comes from the pores. So all the compounds that were inside the pores of the glasses. Then in another study, they considered the functionalization of male-derived glasses with compounds of Rosa canina bud extracts. So here it was quite interesting what they did at the beginning, because they kind of made a surface activation. So this was to expose the hydroxyl groups in the surface, and then they could have a better attachment of the plant, the derived compound. And and this was kind of done. So due to these anti-inflammatory and antioxidant properties of these bud extracts. And here there is another example of surface modification. So this surface modification was done to allow a better loading of the drug or the medicinal compound here, this Boswellia sacra. So they did a quite nice study with BET when they showed that when you have this functionalization, the pore size and the surface area of the nanoparticles, because here they use nanoparticles, increased. So then this allowed to have a more sustained release also of the compound compared to the particles which were not functionalized. So yes, here the authors also showed antibacterial properties, especially against gram-positive bacteria, and they observed really a dose-dependent effect. So depending on the concentration of the compound, they had a higher or lower activity, but this is quite expected for either ions or medicine compounds, herbal medicine compounds, sorry. So Moreover, the use of icarin has been quite studied as well, but in this case it is on bioactive glass scaffolds, and here a polymer was used as the carrier of the drug. So they worked a lot on the optimization of this polymer for the release of the icarin, and yeah, like for example, cross-linking the gelatin and so on, so that the coating was not degraded fastly. And yes, finally, here there is an example of for cancer therapy. So silivinin has been studied as a tumor suppressor. And here they use mesoporous bioactive glasses. They load them with this silivinin, and they tested again with the breast cancer cells. And here they also show a concentration-dependent effect. But the positive part was that the lowest concentration that they found had an effect is a much lower dose that was reported in the literature. So this was quite successful for them, and then showed a great potential for cancer therapy. So now I would like to move to a study that we did in our lab, and this is with Manuka honey. So in here, bioactive glass was used to produce scaffolds, and then we had a coating with Manuka honey and cyne. So in general, honey, all kind of honey, let's say, possessed antibacterial and antioxidant activity. And due to the multiple mechanisms of action, it is hard for bacteria to get resistant to it. So there are mainly two mechanisms, for example, hydrogen peroxide formation and also low pH. But in the Manuka honey, there is also another mechanism, which is the compound of methyl glycoxal, which is kind of the main active component of the honey. And that is the reason why when you get this honey in in a drugstore, for example, or everywhere now, I think you can find this quite easy because it's getting much popular. You have, like, the price depends actually on this MGO content. So yeah, it is supposed that the higher this content, then the higher antibacterial effect the honey should have. And then we have cyne, which is a corn protein, and here was used, kind of to help carry the honey as well. And yeah, it was used because it has a great film forming ability. So for this, the process of the production of the scaffolds was through the foam replica technique. So in here, polyurethane foam is dipped in a slurry containing bioactive glass powder and a binder, so in this case PVA. And then this is sintered to densify the structure, and of course to burn out first the foam and then to densify the structure. So here we can observe the glass scaffolds, and after the coating, we have this yellow color, which is given by the cyne. So here we can have a closer look on the coated scaffold. So we observe that that we have still a porous structure, but with few blockage, so pores that are blocked. But in general, we can see a good coverage and also a smooth surface. And then on some pores, we can see this kind of cracks from the cyne. Then here we can observe the coating containing Manuka honey. So in these SEM pictures, we can see this as the dark spots. So this was quite interesting for us because we could really see the difference when we had or not honey. So it was easier for us to observe this through SEM. And here we also have another example of a scaffold with honey, but with a higher concentration. So we can even see it at the lowest magnification, which we couldn't when we had a lower amount of honey. And of course, we also analyze the coating with FTIR. So in here, we can observe that for the glass spectra, we have the typical silicon-oxygen bonds. Then for the sign spectra, we have the typical peaks for proteins with different amide groups. And for the honey, we can see peaks which are characteristic of carbohydrates. But our idea was to see if we could identify the presence of honey in the scaffolds with this method. So on the right, on the lower part, we can see the different scaffolds. So the scaffolds with sign, the scaffold with sign and honey, and also the glass scaffold. And then we could detect that at around 3,200 wave number, we have the peak characteristic of the honey. So then we realized that through this method also that the honey was present in our scaffold. So we also performed the bioactivity test to see if there was an effect of the coating or the presence of honey in the formation of the hydroxycarbonate layer. So here we can see that after 1 day or 3 days, mainly the degradation of the coating is happening. But after 7 days, we can already see good coverage of the apatite layer, which we could also observe, of course, after 14 days and also 3 weeks of immersion in SBF. And here I also showed the FTIR evaluation. So in which first we have the peak corresponding to the formation of this silica-rich layer, and then also the characteristic peaks of the phosphate groups. So of course, one of the idea when we have these natural compounds is to know the release of the phytotherapeutic. So in this case, we were studying the release of Manuka honey, both with UVVs and also with FTIR. And we didn't see good results here. So, and this is because the honey was released very fast. So you can see that after 1 hour, all the honey was basically released. So we started trying to optimize this system to see if we could get a better or a more sustained release, let's say. So then for this, we started working on another coating. So here we use gelatin and we cross-linked gelatin with caffeic acid. So we can observe better results. Here is the release during a period of 1 week. So it's not anymore released like the whole amount is released in the first hour, but here we have a more sustained release, and here we can see the release during the first day. So it's quite different compared to the coating with sign. And here we could also see that it was possible to have a higher amount of honey released from the scaffolds compared to the previous case. So here I just showed the results of the antibacterial studies using metabolic test and also colony counting, and we can clearly observe a reduction of bacteria, especially at the highest concentration of honey. So this was quite positive for us that we could see this effect here. And but then we kept working on studying the biological effect of the honey. So kind of the idea was to study it alone so that we could find like the proper concentration that we could expect from the scaffolds, released from the scaffolds that could be beneficial for cells, but then toxic for bacteria, let's say. So then here we have some results of this experiment. So different concentrations of Manuka honey were tested, and we could see that, so the same concentrations were used for both studies, and we can see that for the cells, our limit was kind of around 50 milligram per milliliters, and but then for the bacteria, we found that after 24 hours, even a lower amount was toxic to them. So this was quite useful for us to keep investigating on this topic. And then we continue trying to combine different concentrations of honey and also different concentrations of the dissolution products from glasses, and then analyze if we could observe a synergistic effect of when we combined both. So in this case, we were not using any more scaffolds. We were just using the dissolution products of the glass. But these are in preparation for the results are in preparation for publication. So I don't show them here, but what I can say is that in general we didn't observe really an effect on cells, but we could really see an effect on the bacteria when both were combined. So let's say when we have the bioactive glasses alone, they had until certain extent an antibacterial effect. But when we combine this with the honey, it was much higher than the honey alone or the glass alone. So this was quite interesting for us. So yeah, with this, I would like to conclude my talk. I hope I could convince you that bioactive glasses are quite interesting materials for tissue engineering applications, both for soft and hard tissue. That the therapeutic potential of glasses can be enhanced by the incorporation of interesting elements like ions or using natural-based compounds. That herbal medicine brings nature and science together to explore the possibility of optimizing the therapeutic effects of current biomaterials with intrinsic benefits of phytocompounds. And however, it remains a challenge to understand the chemistry and synergy behind the multiple active compounds of phytotherapeutics, and then their translation to get standardized and safe products. So yes, with this, I would like to thank you for your attention, also to the students that were part of the results shown here. And yes, I'm open for questions then.
Thanks a lot, Marcela, for your great talk. It was very interesting. So now it's time for questions for both Valeria and Marcela. If anyone has a question, you can write in the chat and we will ask them directly. I don't see any question yet, so we can go for questions. I have a few. I don't know if Maria has some questions or other people. I just see one in the chat. Okay. So a question for Professor Cannillo. So what is the difference between the amorphous BG MS10 glass and crystalline biosilicate glass ceramic in terms of bioactivity and mechanical strength?
Okay, thank you very much for the question. When the bioactive glass is crystallized, the bioactivity is less pronounced. So when you crystallize the bioactive glass, the glass I show you, you lose some bioactivity. On the other hand, as far as the mechanical properties are concerned, you can obtain a little bit better mechanical properties, such as Young modulus, if a product is crystallized. However, on the overall balance, the amorphous product is better, because even if the mechanical properties are a little bit less good, the bioactivity and biological response are much better. So definitely it's better to have an amorphous bioactive glass. I don't know if this is enough as an answer or...
I don't know, but thank you for your answer.
Okay.
Thanks. Yes. So there is another question for you. So during the SBF test, did you have to change the solution during the immersion period?
Yes, the solution was refreshed every 2-3 days. Yes, depending on the experiment. This is stated in the seminal paper, which defined how to do this kind of test. So yes, you have to change to refresh the solution. Yes.
Okay, because Mara has some issues with the calcium carbonate precipitation on the surface rather than epoxyapatite. So I guess it comes from the
Yes.
refreshment. Okay, great. Is there any other questions? I don't know. So I may have a questions also for you, Valeria.
Yes.
What are the biggest challenges right now for bioglasses in order to go from the scale of the lab to more like commercial products for patients and surgeries?
Yes, that's a very interesting question and a very difficult point to tackle, because at this moment we are trying to find a company which wants to buy the patent and commercialize it, because of course, as you know, we are a university, so we can just produce lab scale samples, so we can produce a few grams. Of course, we don't have a potentiality to produce something which can be sold. So you can arrive till the stage in which you have preclinical studies, and then for sure you need a company. You need a company to buy your idea and then commercialize it, like it was done for the original hench composition, the 45S5. There is a company behind it. Marcela gave a very nice overview of a commercial product like Novamine, Novabone, or of a toothpaste. So at some points you can obtain very good results, but at some points you have to have a company which want to buy the idea and then commercialize the product. So we are not in this stage yet. We are trying to find a company for this.
Yeah. What would be ideally the best synthesis process to produce big quantities?
I think melt quenching is still the better option, because you know there are many bioactive glasses produced by sol gels, but you obtain just a few grams. So with melt quenching, if you have a platinum crucible which is pretty big, and you can, of course, you can put many crucibles in the same oven, you can produce many grams per batch. But that is it, in my opinion.
Okay, thank you.
Thank you.
Is there any other questions for two speakers?
If nobody has any question, well, I first would like to thank to Valeria and Marcela for accepting the participation in this webinar, and also for the nice presentation you did it. I was coming back a little bit to the multidisciplinary side. Seems that one of the challenges in the next years for biomaterials will be focusing the antibacterial activity because of this bacterial resistivity and so on. And I was curious about if you think, for example, the present protocols to test the antibacterial activity facing a bacterial resistivity are suitable, or maybe we are really not prepared for test this antibacterial resistivity and the potential of the biomaterials developed for this challenge.
May I answer? It's a very interesting question. I don't think there is a standardized protocol. There are, of course, many studies in the literature, so you can try to do the same protocol as another researcher. And I agree with you, this is a very, very important point. For example, as I mentioned, for skin regeneration, of course, you need an antibacterial effect. Otherwise, you get infection. So this is a very important issue. I don't know, maybe Marcela can answer as well, but I'm not aware of any standardized procedure yet. So that's a very good point to bring to the attention of the scientific community. Maria, thank you very much for this idea. Maybe we can discuss and, I don't know, think of something.
Yes, I think I can add that there are, so it depends also a lot on the type of sample that you have. So it is not the same testing powders or testing pellets or also the amount that you test. So I think it is not easy to really compare results also in the literature, because everything is done differently. But that is from the materials preparation, right? Then when we have the different bacteria strain, then this is also totally different. There are some that are maybe more relevant than others, or are more recurrent, and maybe, well, or talking just about our lab, let's say we have just the kind of basics bacteria strains that we could kind of do a first assay to test the materials, but of course there is the need to do deeper studies, or more relevant for really having a better idea of the antibacterial effect of materials. But definitely it is also a difference. So there are, for example, in the case of glasses, sometimes we need to have the powders immersed in liquid to really see this effect, for example. So yeah, it depends a lot on the sample preparation as well.
Okay, thank you so much.
There is another question about the drug release from the bioglass. Maybe Marcela can answer. How do we ensure the loading and persistency of the drug, and how we analyze the dissolution rate and the loading of the drug?
Yes, so usually, well, it depends on the method that you use to detect it. So one that is quite used, because it's also maybe easier to have it in a laboratory, is the UV-Vis compared to the chromatography, for example. So then when you have a drug that that you can detect with a certain wavelength, so that you have a clear peak at a number, or like that the active component is giving this peak, then it's much easier to detect it. So okay, that is kind of the first point to really detect the drug. So then usually what we do is that we have a known concentration of the drug. Of course, we have to prepare calibration curves, so with certain concentrations, so that we are sure that the amount that we are measuring is the right one. And sometimes this is not so easy, especially with these natural compounds, because sometimes when you add this in combination with other materials, for example, the pH changes, also the color of the solution changes. So then you have to adapt again everything to have really a precise value. But then you have a known concentration of the drug. Then when you incorporate your particles, for example, mesoporous bioactive glasses, you can either, because of course you can imagine you have a very concentrated solution with the drug, then you put your particles, then you wait for how long you need to wait, or your protocol is, and then you get your powders with the drug inside. But of course you have a much lower concentration that you have originally in the solution. So one approach is to dissolve completely the drug that is on your powder, so that you have a known amount of powder, and then you dissolve it completely, and then you measure in the UV-Vis, for example, and then you can have a correlation with the concentration that was released. And then this, you can say, okay, this was the drug that was completely absorbed by the fixed amount of material. This is one approach. Of course, there are different approaches for that. I hope I answered the question.
Thank you, Marcela. I think the answer was very complete. I have one more question for you, maybe just like curious. Do you think if you try different kind of honey from different regions, it will change a bit like the properties? Have you
Yes,
tried that?
definitely.
Okay.
Because even just using different type of manuka honey, so with this MGO content of different values, we can have different effects. So there are already some studies using different type of honeys. I think in Latvia, in Riga, they are doing a quite deep study on this topic, but it's definitely different. And this is also a disadvantage of this, because to guarantee the source, this is very difficult. So in our case, what we did, okay, for the first trial, we bought the manuka honey from the store, like as you can buy it now. But when we saw, okay, this we could be interesting, then finding a company that could give us a certificate of the quality of the honey, and that we can maybe have more like reliable results, this is also different. So and with these natural compounds, this is usually the case, that the source, if the source is different, then it's likely that the results might change. So that's why it's important to have a standardization for this.
Yeah, for sure. And also it can change between the seasons. I know that the honey can change like the color and so the composition. So yeah,
definitely.
very interesting. Yeah, thank you so much. I don't know if you have any other questions from the audience, from the panelists. If there is no other questions, I would like to thank again very much Valeria and Marcela for their great talks today, and to accept our invitation from both the YCN and the Bioceramics Network. It was a very big pleasure for us. Welcome you.
Thank you to you for your invitation. So I would like to thank you.